Alrighty, so we brought in a guest lecturer today for our lecture on Markov Chains and Markov models. He also contributed to the Twitterbox tutorial that you've all been doing. You heard during orientation the stories of the iPhone game that I launched when I was in college at MIT. And Daniel wrote basically all the code for that. He was my partner in crime at the time. I actually met him in the same class that I met Ashu in high school. So we went both to high school and to college together. Daniel stayed at MIT, took the wise path, and is now pursuing his PhD at UC Berkeley. Daniel kind of got me through all my math classes in college, and also, picked up iOS development with no prior knowledge and built, professional grade software. So it seemed like a natural fit to bring me, especially because I've witnessed from a long time ago that Daniel is a born teacher, and actually my first ever teaching experience was co-teaching a class with Daniel to a group of middle school students when we were both in high school as part of the volunteer project. So he is endlessly knowledgeable, and I'm really excited to have him here. And he's going to be giving our lecture, and we'll probably find a way for them to get in touch with you afterwards if they have follow-up questions.
Yeah, absolutely.
And if you like him, let us know and we'll bring him back. I want excuses to bring him back. All right. Thanks so much. Take it away, Daniel.
Okay. Thanks, Jeremy, for the nice introduction. So I'm Daniel Fremont. I'm happy to be here presenting today. Please let me know at any time if you have questions. I'm going to be doing this in a pretty informal manner. So just raise your hand, and if I don't notice, wave it around or just yell out. Right, so the topic I'm going to be addressing today is Markov chains, which are sort of a really fundamental mathematical object that has been around for over 100 years now, but has been used in many, many different applications. I'll mention some later on. But there are a lot of important pieces of software out there which internally are using Markov chains. And I'll hopefully give you a sense of why they might be useful today. In particular, this is in the context of this project you're working on for generating random sentences. So one of the main uses is Markov chains is in generative processes like producing random sentences or music even, anything like that. So I'm going to start out with sort of an overview of some basic probability. I know you guys saw some of this a while back, but I'm going to go into a little more depth now. And if everyone is okay with it, we'll just go through it quickly. But if we need to spend a little more time, that's totally fine. And then we probably will have a break before getting on to the actual stuff about Markov chains. Okay, so to start off with, as I said, a little bit on probability. So I want to define this a little bit formally. Of course, you all have some intuitive notion of what probability means. The probability of something somehow represents how likely that thing is to occur. But of course, in order to do mathematics using probabilities, you need a rigorous definition. So I'm not going to go completely down to the level of axioms, although it can be done. If you're interested, ask me afterwards. But I want to just introduce a few of the terms that are used, some of the fundamental concepts, because you may see these later on. So one is this notion of a sample space. So one way of defining probability is you have in mind this space of sort of possible worlds. They're the different states the world could be in. So the world here is just whatever system you're interested in. So if you're interested in reasoning about a die, you're rolling a die, then it might just be the 6 possible outcomes of that die, say. And so the sample space consists of those. So here, since the most important world is World of Warcraft, obviously, I've picked a Dungeons & Dragons style 8-sided die. So the sample space is this green thing, and there are 8 different worlds in it in which the die comes out 1 through 8. Okay. And so once you've set up the sample space, the sort of primitive objects that you'll assign probabilities to are called events. So in every world, an event can be either true or false. So one event could be the die roll comes out odd. And that's true in these highlighted worlds here. So out of the 8, there are 4 worlds in which that event occurs. The other 4, it doesn't occur. And so we say the probability of this event is 4 over 8. It's just 1/2. So in general, the probability of an event is just a fraction of the worlds in which it occurs. And this, of course, makes sense for any kind of event which is, well defined in terms of what's going on in each world. Okay. So, there we go. Okay, so this way of talking about probability may be a little bit different from the way you've seen it talked about before. Often, people talk about random variables having some distribution. Like you might say, okay, this die roll is a random number uniformly distributed between 1 and 6. And there doesn't seem to be anything about events going on there. So it's really an equivalent way of looking at things. It's when you say the die roll is uniformly distributed in 1 to 6, you're really talking about 6 underlying events. The event of the die roll coming out 1, coming out 2, etc. And when you say it's uniformly distributed, you just mean each of those events has equal probability. So like if we say something like the variable token is uniformly distributed over these 3 strings, it's saying that the event of token equaling this string has probably 1/3, the event of it equaling that is 1/3, and the event of it equaling this is 1/3. So underneath, it's just events, but random variables and distributions is a convenient way to talk about things because often you want to use random quantities in the same sort of way you would use a non-random quantity. You want to be able to plug it into an equation or something like that and just treat it like an ordinary value, and then you can just use these random variables for that. So yeah, in general, a distribution is just a function which says for each event that says, the variable has this value, what probability that event has. And we're just going to be talking about discrete probability distributions where the number of possible outcomes or values of the variable is finite. So the die roll could be 1 through 6. It's not like any real number between 0 and 1, for which there would be infinitely many possibilities. Defining that is a little more complex, and we won't get into it here. But if it's a discrete distribution, then you can think of it in terms of that possible worlds picture I showed before, where you just have finitely many worlds. Okay. All right. So once we've defined some events, a natural thing you want to do is work out the probability of combinations of those events. So like here we have 2 events. The die roll comes out odd and the die roll comes out prime. So you may or may not be able to see these colors. But on the picture here, I've done in this sort of pink region the worlds in which the event rolling odd comes out true, and in blue, the worlds in which the die roll comes out prime. Okay? So each of these, sorry, I'll be a little louder. So each of these clearly has probability 1/2, right? Because it's true in 4 out of the 8 possible worlds. But what's the probability of rolling both odd and prime? So the numbers which are the worlds in which the event odd and the event prime are simultaneously true, it's just the intersection of these 2 regions. So it's these 3 numbers out of 8. So the probability is 3/8. So in particular, it's not so clear how you would get that from the 1/2s here, right? Another example that's even clearer, what about rolling either odd or prime, right? There you might think maybe we can just add up. Okay, probability of getting odd, probability of getting prime. We would get 1, but that's clearly not the answer. What's the answer here? Someone? 5/8, right? Because there are 5 worlds here in which at least one of those 2 events holds, okay? So combining events is not just a simple matter of adding together individual probabilities. So how do we do that? So as was suggested, we can think about 2 events being true at the same time as being some kind of intersection. So the way to see that is to think of events as sets of possible worlds. So the event where the roll was odd is this set of possible worlds, and this set here corresponds to the event of rolling a prime. And so the set of worlds in which odd and prime are both true is just the intersection. So this is the symbol for the intersection of two sets of the set corresponding to odd and the set corresponding to prime, right? Because it's just the worlds in which both of those events are true. That's what the intersection means. The intersection of two sets is just the set of elements common to both of the sets. And similarly, if we want to have either odd or prime, that's the union of the two sets. So that's any world which is in one set or the other set, or both. Okay? So that gives a nice interpretation of events as sets of worlds. But that doesn't clarify necessarily how we can compute the probability of these intersections and unions given the probabilities of the individual sets. So how can we do that? Let's look at the case of OR first. So for this, there's a nice formula which is called the inclusion-exclusion principle. And this is just a special case of it. I can talk about the more general one later. But here's the thing to notice is I've written in red here the region in which one or both of those events was true. And it has 5 possible worlds. The two sets making it up each have 4 possible worlds. And the intersection, the worlds in which both events are true, has 3. And so you notice if you add these two up, you can't just add them up because you get something that's too large. But if you subtract off the intersection, then you get the right number. And the reason for this is that when you count everything in the pink region, you're also counting, of course, everything in the yellow region because it's part of it. But when you count everything in the blue, you are again counting that yellow region because it's also part of that. It's the intersection. It's in both of them, right? So you're counting the things that are in the intersection, the worlds in the intersection twice. So what you need to do is subtract off 1 copy of that intersection, and then everything in the pink but not in the yellow will get counted once. Everything in the blue but not in the yellow will be counted once. Everything in the yellow will be counted twice, but then you subtract off 1 copy, so it ends up only being counted once. Okay? And so in general, what that means is that the probability of one or another event, or both, happening is just the probability of one of them plus the probability of the other minus the probability that both. Okay? Does this make sense? Okay. So a couple things to notice here. One is that sometimes we don't need this second term. Sometimes you can just add the 2 probabilities. So when can we do that? Yeah. Right. When they're mutually exclusive. So if this pink and the blue set had no worlds in common, right? There was nothing in this yellow part, the intersection, then you could just add them up because you're not counting anything twice, right? So that's often, it's a convenient thing to remember that if you have 2 mutually exclusive events, you can just add their probabilities to get the probability that one or the other happens. Yeah? Right, that's true. So a good point was made just for those of you who may not have heard. Even when they are mutually exclusive events, you are still this formula is still true. You should really subtract off the intersection. It's just that in that case, the intersection is empty, right? There are no possible worlds which satisfy both A and B if they're mutually exclusive. So that's why this formula simplifies down to just the sum. Good point. Okay? Now, I've given it here for, A or B. You might ask, what about A or B or C, some third event? It's pretty simple. You can try working it out yourself to see how this formula changes. It's an interesting exercise to try for 3, for example. And if you want a little bit challenge, try driving it for any number of events. So that's that's the general inclusion-exclusion principle. It gets a little bit more complicated than this, but there's a nice pattern, so you can try working that out. Okay, so now we figured out how to compute the probability that one or the other, or both, of a couple of events holds. But that still leaves the question, how do we compute the probability of 2 of them holding simultaneously? We need that to use this formula in the first place. Okay, so right. So The problem here is that the probabilities of the individual events in general don't give you enough information to figure out how often both of them occur at the same time. And this quantity, the probability of them occurring at the same time, is called the joint probability, just because they're happening jointly. It's usually written this way, probability of A comma B. So that just means A and B. And to give an example of why you don't have enough information, just given probability of A and probability of B, let's look at those two events we had before, right? Odd and prime, and a new event, which is that the roll was even. So all three of these have probability 1/2, right? For this 8-sided die we were talking about before. But let's look at the joint probabilities of a couple of these. So the probability of it being simultaneously odd and prime, as we worked out before, was 3/8. Okay? So you might hope maybe there's some formula where you can plug in 1/2 and 1/2 and get 3/8. But you clearly can't, because what's the probability of it being both odd and even? It's 0, right? So again, in both of these cases, the probability was 1/2, 1/2, 1/2, 1/2. But here, the joint ended up being 0, and here it was non-zero, right? So the reason for that is that the joint probability has to do not with just how likely an event is in isolation, but how the events interact with each other. So if one event prevents the other event from happening, for example, that will change the joint probability so that it has to be 0, right? Whereas if one event has nothing to do with another event, then it's certainly possible for them to have a non-zero probability. Yeah, question?
Would the combined information to like figure this out be like the total of each element in each set?
The sizes of those sets, you mean? Yes, so if you have the sizes of all those sets involved, then absolutely, because this joint is just the size of the intersection divided by the total number of possible worlds. But there are many situations where you don't have an exhaustive list, say, of what's true in all the possible worlds. Maybe you just have some limited information about probabilities of specific events, say. And then that's not enough in general to work out these joints. So often what happens when you have a problem in probability is that you're actually given all the joint probabilities, and then you can derive everything else from those. So you might not be given the probability of A by itself, but you can compute it given the joint of A with everything else. We'll see that actually just on the next slide. But first, any questions on what the joint probability means? Okay. And uh-oh. Okay. Right. So as I just said, often the joint probabilities are what you start with. And you can go backwards to get the probabilities of individual events. So these are called the marginal probabilities. That's when I'm only interested in how likely is A. Not necessarily what is going on with B, but just no matter what B is doing, what's the overall probability for A to hold? That's called a marginal. You take the joint and then you sort of eliminate all of the variables except the one you're interested in. And you can see how to do that. Let's say we want to figure out the probability that the roll is odd. Well, I can write that as a sum of two terms. One term where the roll is both odd and prime, and another where it's odd and not prime. So it's clear this covers all possibilities for the die roll to be odd, right? Because the roll is either prime or it's not prime. So looking at the picture here, let me move over here so I'm not blocking it. Looking at the diagram over here, the odd is this pink region again. The prime is this blue region. So the not prime is everything that's not in the blue region, which is hard to draw in one connected thing. So I've broken it into two pieces here. There's this one and this one. So it's clear that the blue and the red together cover everything, right? Because the number is either prime or it's not prime. So if we add together the probability where it's odd and prime, that's these three here. And then where it's odd and not prime, that's just this one here. We add in those two intersections, we get the 4 possible worlds out of the 8, which is gives us the correct probability 1/2 for it being odd overall. People see how this works? So in general, if you want to figure out how what a marginal probability of some event is, you just have to add together all possible terms where you put in all the combinations of the other variables being, or other events being true or false. So here I've gotten rid of the prime part by adding together when it's prime and not prime. If I had a third variable, I'd have to add in, prime and the third thing is true, prime and the third thing is false, not prime and the third thing is true, not prime and the third thing is false. Okay? Because together that will cover all possibilities for the roll to be odd. Okay? This click is not going to work from over there. Okay. All right. So one last type of probability that I want to introduce, this is a very important one called the conditional probabilities. So the idea here is that we maybe know some information about what happened to the roll. Like someone told us it was odd. Maybe, we know the person won the bet and they had bet on odd. So we know that what they rolled was odd, but we don't know specifically what number it was. And then we want to ask, what's the probability that it was prime? So given the knowledge that it was odd, the probability of being prime might change. If we don't know anything, the probability might be one thing. But then given the extra fact that it's odd, that probability could change. So, and then this probability, given the extra knowledge, is called the conditional probability. So this is how you write it. This is the conditional probability that the roll was odd, given, that's what this vertical line means, given that it was prime, say. Okay, I guess I did it backwards from there. But let's see how this works. So what's the probability of it being prime overall? It was 1/2, right? 4 out of the 8 possible worlds. Now, if we know it's odd, that means we know we're in one of the 4 possible worlds in the pink region. So we can just ignore these other 4. Now the question is, what fraction of these pink worlds did it come out prime? Okay? So in here, there's just these 3 worlds, right? It can't be in 2. It can't be in world 2 because we know we're in the pink region. So the probability here is, well, it's given by the 3 possible worlds in which it's prime out of only the 4 that are consistent with the knowledge that we have, that it was odd. Okay? So the fact that we know it's odd means we can restrict our attention to just this subset of the possible worlds, and we compute the probability relative to that subset. So in general, the probability of A given B is the probability that A is true and B is true, so that's the inner region, divided by the probability that B is true. Why is that? Because we want to know the probability that A is true given that B is true. So it's going to be the probability that they're both true, but only considered among the possible worlds in which B is true. So you have to normalize this by the probability that B was true. If we didn't do this, right, if we left this off, then we just get the probability that A and B, which would be these 3 possible worlds, but out of the entire 8, which is not what we want, right? Because we only want it in those worlds that are consistent with the knowledge we have, namely that it was odd. So it should be these 3 worlds out of the 4 possible. So the 3 here is the numerator, and the 4 possible worlds we're interested in go into the denominator here. So we end up with an actual probability, conditional probability of 3/4. Because in 3/4 of the pink worlds, it's true. Any questions on that? Okay, excellent point. So the question was, in case people didn't hear, what's the difference between this and Bayes' theorem? Okay, so Bayes' theorem is something which I'm not actually covering in these slides. We can talk about it later if people are interested. But it's a simple but very fundamental theorem in probability theory, which basically relates the probability of A being true given the knowledge of B to the probability of B being true given the knowledge of A. That sounds like, why would you care about the relationship between those? But it turns out to be a very useful thing in a lot of computations. Like the classic example is you have like a drug test or something like that. And you know if someone tests positive, then they're like 90% likely, maybe, let's say it's a drug test and you know that it has only a 10% false negative rate, right? And you also know that it has a 5% false positive rate. and you want to work out the probability, given that someone tested positive, what's the probability that they were actually using drugs? This is an unintuitive calculation because even though the test is very rarely inaccurate, there are so many more people who don't use drugs than do that even if someone tests positive, it's actually much more likely that they don't use drugs than they do, unless the test is like extremely accurate. And this is kind of a surprising result, but it comes out if you use Bayes' theorem. We can go through it later if people are interested. Right, so how does that connect to this? So this is just the definition of conditional probability. So the probability of A given B is defined by this formula. Of course, we have an intuition for why this formula is the right formula. It makes sense given this interpretation of impossible worlds, but it's just a definition. Bayes' theorem is what you get if you use this formula and basically then you observe that the probability of A and B being true is the same as the probability of B and A being true, because A and B being true is the same as B and A being true, right? So if you then swap A and B here in this formula and then plug them together, you get Bayes' theorem. So Bayes' theorem is just a little bit more sophisticated, but it's a result that uses this. Bayes' theorem is derived using this definition. Does that answer your question? Okay. All right. So now what I'd like to do, just to make sure that everyone has understood the basic ideas here, is just give you a few basic exercises to do with your neighbor. So there are a bunch of rows of 3, which is a little awkward for neighbors. So you can either do all 3 or face the person behind you or just find someone near you. And if you don't have a partner, you can just go with someone nearby. So here's a new set of events. The same sample space we had before, same 8 possible worlds. But now I'm interested in these 3 events. One is that the roll is a power of 2. So it could be 1, 2, 4, or 8. One is that the roll is greater than 2. That's this blue region here. And one is that the roll is between 5 and 7. That's this yellow ellipse here. Okay? And what I'd like you to do is compute a few quantities here. Joint probability of A and B, and these 3 conditional probabilities. And just to remind you, because I don't have it in front of on the slide anymore, here's the formula for the conditional probability. Okay, so spend a minute or 2 working that out with your neighbor. Any volunteer to present that one? Brave soul. Exactly, right? So remember that probability is in this interpretation just defined to be the fraction of the possible worlds in which the event is true, right? So as you correctly pointed out, there are only 2 worlds in which both A and B are true. So the probability is just those 2 worlds as a fraction of the whole 8. So it's 2 over 8, 1/4. All right? Everyone see that? Okay. So the next one, probability of B given C. Somebody who hasn't answered a question so far? Right? So first step, find probability that both of them happen. Okay? Okay, right. So does everyone see that? So probability of B and C, well, everything in C already has B true. So it's just the probability of C, which is 3/8, because these 3 possible worlds out of a total of 8. Okay, keep going. Right. So by this formula, right, we take the probability of B and C, which we just found was 3/8, divide by the probability of B by itself, which is these 6 possible worlds out of the 8. So that's 3/4. And so we get 3/8 divided, oh, well, okay, I'll just write 3/8 divided by 6/8, which is 1/2, right? Okay? So this is 1/2.
Isn't it 3/8 divided by 3/8 because we have to find the probability of C, not probability of B?
Right. So you see the thing here? So this is the thing to be careful about. The order between these 2 matters, right? And it's the second one, the thing that you're assuming to be true, like the extra knowledge you have, it's that you divide by the probability of. So here we have to divide not by 6/8, the probability of B, but by 3/8, the probability of C. So then we're just going to get 1. Now, does that make sense? Let's think about this. We're saying the probability of B, given that C holds, is 1. Why does that make sense? Yeah?
All the elements of C are in B.
Exactly, right? all the worlds in which C is true are already in B. So the probability that B holds, given that you know you're in this yellow region, is 1. Okay? All right. Let's do it the other way around. C given B. Someone new? Exactly, right? This is just what we were doing before when we divided by the wrong thing by accident, right? So now we're getting 1/2. Now, does that make sense? Well, let's look. Here are the worlds in which B is true. There are 6 of them. And in exactly half of them, in 3, C is true. So the conditional probability of C, given that B holds, is 1/2. All right? Okay, so the last one's a little tricky because I didn't actually define this. But maybe you can guess what this is supposed to mean. Yeah. Okay, it's 0. So what do you think this means, first of all?
It's probability B and A.
Right. Uh-huh. So it's the probability given both B and A, right? So we can have multiple pieces of knowledge that we're conditioning on. So here we want to know what's the probability that C holds given we know both A and B hold. Okay? So how might we work that out? Right. Does everyone see that? So remember, the conditional probability is the probability that both the left and right-hand sides hold. The thing you're wondering about and the thing you're assuming to be true, divided by the probability of just those things you're assuming. So here it's going to be the probability that all 3 of these hold, divided by the probability of just B and A holding. All right? So somebody else, what's the probability that all 3, A, B, and C hold? Shout it out. Better shout it louder. 0, right? Because is there any world that's in the intersection of all 3 of these regions? No. So it's 0. And does this make sense? Well, let's look. Given that you're in A and B simultaneously means you must be in this intersection down here, right? Because these pink worlds are where A holds, the blue worlds are where B holds. So the intersection is where both hold. And now we're saying, given that you're in these 2 worlds, what's the probability you're in the yellow region? Well, it's 0. None of them are in the yellow region. Okay? Question?
Yeah, I had a question on number 3 there. You said the answer was 1/2?
Yeah. Did we make a mistake?
Yeah, definitely.
Uh-oh.
Here's my question.
Yeah.
1/2, I see that that's 3 out of 6 possible events.
Right.
B is your total sample size. We're calculating for them out of B, so basically 6 of the 8 dice rolls, not all 8.
Right. That's what this conditional probability means. If we were just asking, what's the probability of C by itself, then that would be 3 out of all 8 worlds. But here we're restricting our attention. We're saying we only want to know what's the probability of C in the worlds where B holds. So you can imagine, a car insurance company, right? They want to know the probability that you're going to get in an accident because they don't want to have to pay for it, right? But they don't want to just know the average probability that you'll get in an accident because that's over like all people. They want to know the probability that you get in an accident given that you are 23 years of age and have gotten in 4 accidents in the past, and whatever, all the relevant information, right? So they are restricting their attention to just the possible worlds that they know we're already in, and they want to know the probability there. That make sense?
Yes.
Any other questions? Okay, so we're almost done with the basic probability stuff. I just want to go over one more notion, and then we'll do a little example with some code that will give us a chance to do a little more interesting probability computation. So the last concept I want to introduce here is the notion of independence. So we talked before about mutual exclusion, right? This is where one or the other thing can happen, but not both. So there's a very tight connection between those 2 things. If you know one of them happened, that means the other one for sure did not. So the other end of the spectrum is independence. This is where the 2 things don't affect each other at all. So if A and B, say, are 2 events that don't influence each other, then let's look at the joint probability, okay? So the joint probability is equal to the conditional probability of A given B times probability of B. All I've done here is take the definition of A given B and multiply through by probability of B. Okay? So we can write it like this. Now, let's look at this probability of A given B. Well, if B has no relevance to whether A is true or not, then the probability of A given B is just the same as the probability of A, because the extra knowledge that B holds doesn't tell you anything. So that just simplifies to probability of A times probability of B. So you may have seen this if you've done some probability before. If you have two events that are independent, the probability that both of them holds is just the product of the individual probabilities. So when the joint probability of two things factors like this into two parts, probability of one of them times the probability of the other, those two events are said to be independent. They really don't have any effect on each other. So this is very useful when you're trying to compute joint probabilities of a bunch of things. If you know some of them are independent, that can simplify the computation a lot. So for example, let's say I want to know if I flip a coin, I flip n quarters, or I flip one quarter n times, right? Each flip is independent of the previous one, unless I'm like getting tired and it somehow affects my flipping. But basically, they're independent, right? And let's say it's a fair coin. So each time I flip it, I have probability 1/2 of it being heads. Now I want to know, if I flip it n times, what's the probability that every single time it comes out heads? Well, because each of those coin flips is independent, it's just 1/2 for the first being heads, times 1/2 for the second one being heads, times 1/2 for the third, and so on, just n times. So the probability for all n of them being heads is just 1/2 to the n. That make sense? So if they weren't independent, right, this wouldn't work. Because if I flip, let's say I flip the n coins, but something's happening, like every time I flip the coin, like part of it falls off so that it becomes more likely to be heads the next time, something like that. Then the probability of getting n heads in a row would be the probability that you get heads the first time times the probability that you get heads the second time, given that it was heads the first time, right? See this? So that might be different than just the probability of getting heads by itself, because now something's changed. So if you had n coin flips, each one you'd have to use the conditional probability given that all the previous ones were heads. And that's going to be potentially different, give you a different result than if you just took the individual marginal probability of it being heads overall and just took the product of those. Questions on how this works? Yeah, so actually this is a good puzzle, right? Let's say you flip the coin 100 times, right? It comes up heads every single time. What's the probability it's going to be heads the next time? 1/2, right? So this is called the, okay, there's various gambler's fallacies, right? But this is one of them, right? If your luck has been really bad, it's got to turn soon, right? Not true if they're independent, right? If they're independent, it's going to be the same every time. So the fact that you've gotten 100 heads, it's true, that's extremely unlikely, but it doesn't have any bearing on what the next roll is going to be. And that might seem unintuitive because you would think, probability of getting 101 heads is super low, right? But actually, the probability of getting 100 heads and then another head is the same as getting 100 heads and then a tail, right? So the marginal probability on that last roll is just 1/2. Yeah?
I was more thinking about the joke that it's just a two-headed coin.
Oh, okay, yeah, that could be another problem. If your coin is heads on both sides, yeah. Yeah, I mean, coin flips are like a standard probability thing, but people have actually done this. There was a guy who was in a prisoner of war camp in World War II, and he spent a lot of his time flipping coins, and he wrote down the statistics. Turns out it's close to 50-50. He did it like tens of thousands of times. Yeah, but there's an interesting paper by a mathematician who used to be a magician before becoming a mathematician, and they filmed people flipping coins in high-speed cameras, with high-speed cameras, and the guy can now reliably flip a coin so it always comes up heads. So don't bet against that guy. But anyway, it's an interesting question of how the probability of coming up heads depends on how exactly you toss it. It isn't just a fair coin, because it depends how much spin you put on it, so forth. All right, but for our purposes, all coin flips are fair and independent. Okay, So now a little implementation exercise that might be interesting. So before, when you were working on stochastic sampling, I think you implemented, most of you hopefully have implemented something like this. You're given a list of tokens from the corpus that you've been working with, and the probabilities, how often this token occurred each time, okay? So I guess I should say, sorry. So if each distinct word is a type, right? And each occurrence in the text is a token. So we counted up all the tokens. We saw this particular type occurred 4 times, say, out of a total of 1,000 tokens. So its probability is 4 out of 1,000. And then the question is, how can we sample from that distribution? Idea being that this will give us text that's more like the original than if we just picked words uniformly at random, because some words are much rarer than others. So here's some example distribution. The word the has probability 1/2, best 1/8, times 1/4, and worst 1/8. Okay. So one way of doing this, which you may have seen before, we can write like the following. We make a list of all the tokens. So in particular, if a type, a particular word occurred multiple times in the corpus, it's going to occur multiple times in this list. So here the occurs 4 times, best only once, worst only once, and times twice. Why would we want to do that? Well, now, if we uniformly sample from this list, we're going to get the right probabilities. Because if we pick a random one of these indices, we're going to get the 4 times, right? So we can just do this way. Here's the randint function, which picks a random integer uniformly at random between the 2 endpoints you give it. So here we're saying we'll pick one between 0 and the last index in the list. That's the length minus 1. And we return the item at that index. Okay? So let's look at one of the events. Say that the sample that we compute at the end is the string the. Does this have probability 1/3? No, it doesn't. That's a typo. Wow. Okay. Can we verify that this has probability 1/2? Okay. So that's one way, right? This is a Monte Carlo simulation. You run this 1,000,000 times, you get different random numbers each time, and you look at the probability, the empirical probabilities. So if I ran it 1,000,000 times and I got the, 500,017 times, okay, it's probably pretty good. So that's certainly a quick and dirty and easy way to figure out what the probabilities are roughly like. And in scenarios where you have a very complicated program and it's very hard to analytically, work out exactly what it's doing, that can be a viable option. But in this case, this program is simple enough that we can actually prove exactly what the probability of getting the is. So, any ideas? Yeah.
Just count the occurrences of the over the total number.
Okay, and why is that equal to the probability that we're going to get that string? So you have the right intuition, of course, right? The more times it occurs in the list, the more often we're going to return it, because we're picking a random element of the list. But let's see how we could, reason about this formally. So what is this randint function doing? It's returning an integer between 0 and the length of the list, which is in this case what? 8. So it's returning something between 0 and 7. Each one, 0 through 7, has equal probability. Okay? Now, we can think of those 8 then as being, say, our possible worlds. In how many of those possible worlds is the sample we're going to get the string the? 4, right. So, yeah, 4, because we're picking 0, 1, the indices are 0, 1, 2, 3, 4, 5, 6, 7. So if each of those comes up, each of those is a possible world. In these 4, the string we return is going to be the, and the other ones it isn't. Okay? So assuming that this randint function actually returns 0 through 7, each with equal probability, we're going to get the 4 out of those 8 numbers it can return, and so the overall probability of getting the is going to be 1/2. Okay? All right, so what's a downside of this approach? Yep. It takes time, okay, but any way of doing it is going to take time. What's particularly bad about how much time this one takes? Right, you have a lot of tokens. So let's say we have we're training our model, which we'll see later, on a real corpus, like the text of Wikipedia. or something like that. There are going to be a lot of tokens. Vastly more tokens than there are going to be types, right? Wikipedia has many, many, many words, but only a relatively small number of them are distinct, because English only has so many words. I don't know, 100,000, something like that, maybe. Whereas the number of tokens in the whole text of Wikipedia is way bigger than that. So if our list here has to have one entry per token, it's going to be a massive list. Can we make it shorter by using a list that only has one entry per type? So that leads to another attempt. So here's how this attempt works. We only have the types, the, best, times, and worst. We don't have to duplicate the, but we're also going to keep track of the probability of each one. So the has probability of half, best 1/8, times 1/4, and worst 1/8. Okay? And here's how we're going to sample. We're going to enumerate this list. Oh, I don't know. Have you seen the enumerate function in Python? Haven't seen that? Okay, good. All right. So we're going to enumerate this list. And for each entry, we're going to pick a random number. Now, this random function returns a random floating point number between 0 and 1, uniformly at random. Okay? We're going to generate such a number, and we're going to check, is it less than, or at most, the prob from that entry in the list? If so, we're going to return it. So let's see what's going to happen here. We're going to look at the first element. That's 0.5. We generate a random number. If it's less than 0.5, we return it. Seems good, right? Because this thing is generating numbers uniformly at random between 0 and 1. So the probability that it's less than 0.5 is 0.5, right? So with probability 1/2, we're going to return the. Otherwise, we go on. We generate a new random number. We check, is it less than 0.125? Probability of that happening is 1/8. If so, we return it, etc. We keep going. Now, it might be that we fail every time, so we put this whole thing in a while loop. So if we get to the end, we'll start again from the beginning. Okay? Clear how this works? So, does it work? Does this return the string the with probability 1/2, best with 1/8, etc.? No. Why not? So you see what's happening here? So the first number, it's true. We check with probability 1/2, we're going to return it, right? But that's not the probability that we return the. That's the probability that we return the on the first iteration of this outer loop, right? If we fail on every one of these, we're going to come back around to the, and it's going to get a second chance to get returned. So we're actually going to return the with probability a little bit bigger than 1/2. Because there's some probability, it's small, but there's some probability that this check will fail, this one will fail, that one will fail, this one will fail, and we'll go back, and this one will get a second try. So you're right, the numbers that are early in the list are going to get returned more often. So let's see if we can work out how this works in a simpler example. Yeah? Right. Yes. So that's another way of doing it, which we'll come to in just a second. Absolutely, that one will work better. But let's first, just for an exercise, go through working out what's wrong with this one. So, there's another thing which you didn't mention, but there's also some issue of we have this infinite loop. So it looks like this might go on forever, right? So interesting exercise, if you want later, prove this program terminates with probability 1. So it's possible for the loop to go on and on forever, but it has probability 0. So every time you go around the loop, the probability, you have a constant probability of exiting. And so you do this over and over and over again, the probability that you still have failed to exit goes down to 0. Okay. So let's do a simpler example. We only have two guys, both with probability 1/2. So the probability that A is returned is 1/2, because you can return the A the first time through the list, plus another term. Let's say you fail the first time. So it's half probability that you return it on this line. The other half, you go on to the second item. So this is this term. Then let's say you go on to the second item, but now you fail the B. So that's also 1 minus 1/2. And then you succeed when you come back to A again for the second time. You return it there. So you see, I'm multiplying these because they're independent events, right? The fact that you failed in the first one doesn't have any bearing on whether you fail for B in the first round, right? Because we're generating a new random number. So we have this term. Then in the next term, it's also possible that we fail on A, fail on B, fail on A again, fail on B, and then succeed on A. So we're going to have 4 of these terms, then the final success. Okay? So we get this infinite series for the probability of A. See where that comes from? Okay? So since I'm not going to go through this in so much detail for time, but basically you write this out as an infinite series. You can factor it a little bit so that it's just of the form 1 plus a number squared, etc. That's called a geometric series. And there's a nice formula. Basically, this series, even though it goes on forever, it converges. You can see by the area of these squares. Like this is a square with area 1, 1/4, 1/16, etc. You can use the formula for geometric series to see that this has value 1 over 1 minus 1/4. And so what you end up getting from this is that the probability that A is returned is 2/3 instead of 1/2. So this method doesn't work. Okay. So one last try, and this is the method that was just suggested. Instead of keeping the probabilities in here, we'll keep the cumulative probabilities. So we'll have 1/2, then 1/2 plus 1/8, that's the probability of best. Then that cumulative probability plus the probability of times, 0.25, etc. And then what we do is we pick one random number, and we go across the list and we find the first element where the random number we chose is less than that cumulative probability and return that one. So if we get something less than 1/2, we return the first guy. Less than 0.625, but greater than 1/2, we return best, etc., the second one, etc. And you can see that the probability that we return a number is just equal to the gap between its cumulative probability and the one before, right? Because if we got something less than the one before, we would have stopped there. But otherwise, we've gone on. And now we'll only return times if we have something between this and that. So you can see that anything will be returned with the right probability because the gap in between these lists exactly corresponds to the actual probability of that string. Okay? Also, this is faster since we only need to generate one random number. And we don't need potentially many iterations of that loop. Okay? All right. So I want to stop with and give you guys a little break here since we've been going for a while. But before that, are there any questions on any of the materials so far? Probability, the definitions. Okay, so let's just take a couple minutes break. Okay, so now we can actually get on to the interesting topic, which is Markov chains. So now we've got the necessary background in probability, hopefully. So going back to the project, we're trying to generate these sentences. So far you've seen how you can learn a distribution over types by counting how many times each token occurs in the corpus. And this is better than just purely random generating words because at least rare things don't come up too often, right? If you just picked random words out of a dictionary, it won't look anything like something real someone wrote because most of the words are going to be obscure things you've never even heard of. Now, how do we generate a sentence from that? Well, if we have n words, if we want a sentence of n words, we just sample n times from this one distribution. You know, the word the is the most common word, say. That might come up. We sample again, pick another word. It's going to be a common word, probably. It might be the word be or something like that. Problem with this is that successive words are independent, right? So if the is the most common word, the most likely pair of words to generate is going to be the, because you generate the first word, most likely word is the. Generate the second word, same distribution. Most likely word is still the. The problem is, even though the word the is pretty common in English, the phrase the is almost non-existent, right? So your thing, even though you're using probabilities, it might be better than just a plain old random dictionary picking thing, but it's still going to look weird. So what's going on there? The issue is context, right? The word the is common overall. The marginal probability of having the word the is high, but it's very rare after another the. If you know that you've just seen the word the conditional probability of getting another the is very low. Another example, the word Zappa is pretty rare, but if you've just had the word dweezil, it becomes much more likely, right? So can we improve our generation procedure to model context like that? Okay? So the idea here is we want to use a different distribution depending on what the last token we generated was. So if we just generated the word the, in the new distribution we're going to use, the word the should be pretty unlikely. And the way we're going to do that is by using a Markov chain. So a Markov chain consists of two parts. It's got states and transitions. So states are usually written in, we usually draw these as a graph, where the nodes are the states, and the transitions are edges. So it's a directed graph. They've got arrows. And each transition has a probability. So this is a Markov chain that might describe, what you are doing right now, possibly. Maybe when at the beginning of this lecture you were alert, and with probability 1/2 you stay alert, as time goes on. But there's some probability you get bored, 1/4. Now, once you're bored, there's a half probability you go back to being alert because I just said something interesting. But there's also a probability of 1/2 that you start getting sleepy. And once you're sleepy, there's a probability 1/4 that you actually fall asleep, at which point you're stuck. Probability 1 of staying asleep for the rest of the lecture. Okay? So this is the idea of a Markov chain. You've got these states. You're in a current state at some time, and then given the state you're in, there's probabilities for moving to different states. Okay? And you can see this works because the probabilities going on the edges going out of a particular state always add up to 1. So here, going out of drowsy, we can either stay in drowsy, that's 1/2, we can go back to alert, that's 1/4, or we can go to asleep, that's 1/4. So they add up to 1. So for every state, these transitions define a probability distribution on destination states. Okay? So once you have a Markov chain, that defines what's called a stochastic process, just like a process that has some randomness in it, for generating sequences of states by what's called a random walk. And the idea is just what I described before, basically. You start in some state, then you randomly pick the next state to move to based on those transition probabilities. So if you're in alert, you've got probability 1/2 to stay there, probability 1/4 to go here, probability 1/4 to go here. So you make a move to one of those three, according to those probabilities, and then you do this again. Now the probabilities are different. Now you've got 1/2 to go there, 1/2 to go there. So we just keep picking transitions according to their probabilities, and that moves us around in the Markov chain. So here we might end up being alert, then we go to drowsy, stay in drowsy, then go to asleep, and then we're stuck there. Okay? So a random walk on a Markov chain gives you this sequence of states. Now, notice that each step depends only on which state you're in. So given that I'm in drowsy, there's a probability 1/2 of staying in drowsy. How I got to the state drowsy doesn't matter. All that matters is that right now I'm in the state drowsy. So using terminology we had before, the state at time t, say, step t in this random walk, is independent of all prior states given state t minus 1. Once you know what state t minus 1 was, you know the probabilities for being in state t. The states that you were in at t minus 2, t minus 3, etc. don't matter at all. Okay? This is the important thing about Markov chains. Is it clear how this process works? Okay, so let's talk about some implementation things a little bit about the efficiency of this. So first of all, how fast can we make doing this random walk. Say we have the Markov chain, we are at a certain state, we want to do one step of the random walk. If the Markov chain has like S states and T transitions, say, asymptotically, like what's the worst case amount of work we might have to do one step of the random walk? Yep. S? Why is that? Right. Exactly, right? So, as you said, in the worst case, you might have a state that has transitions going to every other state, right? So then you're going to have to decide between all of those, say. And so it might take you linear time in the number of states to decide how to do that. There might be faster ways of implementing that, but certainly in the naive way, if you have to check between all those different transitions, it could be linear time there. And what would be a good data structure for representing this Markov chain, given that we need to we want to do this random walk on it, picking random transitions and moving according to those? Sorry? A linked list? So how would you store the Markov chain as a linked list? So you'd have, yeah, so there, like in a normal linked list, you just have one outgoing link to the next item, right? Whereas here you could have several, right? So like the probability, in fact, from alert, there are 3 different states we can go to. So you could have a sort of a linked list where you had pointers to the 3 other things, right? So that's basically storing this as a graph, right? For every state, you have a node which has pointers to all the other nodes, and then you also keep track of probabilities for each of them, right? So that could certainly work. Another idea? Yeah.
What if we use the hash table?
Okay.
Where the key is the word.
Okay.
And the value sort of that key is the linked list.
Okay.
Implements it the same way you showed us in the code previously.
Right. So this is another option, right? You have a hash table where you index into the hash table using the state, and what you get out is the distribution of destination states represented in some way. It could be a linked list, say, of all the transitions or some other data structure. You could have even another hash table if you wanted to. That probably is going to have a lot of overhead. You just need some way that, given the state you're currently at, it's fast to access the distribution for the destination states. Because that's what we're doing in this random walk. We're always taking the current state, finding all the transitions, going to one of them, then repeating. For that state, we look up its transitions and so forth. So a hash table would be a nice constant time way of looking those up. Okay. So this is what we do with a Markov chain in order to generate things. How do we get a Markov chain? So here's a Markov chain learned from this very tiny corpus. Everyone can read that? Okay. So let's see how this works. So we start out in the state corresponding to the first token, that's capital A. Now, how often does capital A occur in this corpus? Twice, there and there. And what we want to know is, what are the possible transitions? If we've just seen the token capital A, what are the possible next tokens to see? Well, we can see man, comma, and dog, comma. So we add transitions for each of those 2 possibilities. Each of those transitions from A to man, A to dog occurred once in the corpus, so we give each probability 1/2. If A dog had occurred twice, then we'd give this one 2/3 and that one 1/3. Okay? Now after man, that only happens once. It's always followed by an A, so we go to A with probability 1. Now A is more interesting, lowercase a. Lowercase a occurs 4 times. And there are 4 possible things that come after: plan, canal, panic, pagoda. So we go to each of those, plan, canal, panic, pagoda, with probability 1/4. Okay? And looking through this corpus, for all the possible transitions like that, we end up getting this Markov chain. Make sense where this comes from? So now if we tried generating something with this, we might, so let's say we started at A, we might get A, dog, a plan, a plan, a plan, a plan, a canal, Panama. Right? We do some random walk. You can follow any of those transitions. And you can see, okay, that didn't make a whole lot of sense. But it was better than just, say, outputting A whole bunch of times. Because A is the most common token in this corpus, right? It occurs 4 times. So if we were just doing the stochastic sampling based on token or type probabilities, we would be very likely, I mean, the most common pair of words to return would be AA. But this Markov chain cannot generate 2 A's in a row because there's no transition from A to itself. Because there is no instance of A followed by A in this corpus. That makes sense? The Markov chain can only make transitions that happened in the original corpus. So that's why it's a better model of the corpus than just random sampling from the same distribution is, because it takes into account some context. It remembers what the last word was, or token was, and uses that to pick the next one. Yeah?
How does it decide how long of a chain to generate?
Oh, how long to run this, to do the random walk? That's, you have to decide. If you want to generate a lot of text, you could do a long random walk. And you might run into the issue of, like, what if you get into a dead end like this? So you can experiment when you implement this, different ways of resolving that. But yeah, it's based on how much text you want to generate. Of course, you might not want to stop at some arbitrary point in here. You might want to only stop when you get to a point that ends a sentence or something like that. But yeah, that would require some extra information based on what you're trying to do. Okay? Yeah. So you mean use the information about which transition you took as and use that to influence your decision? So you could certainly do that, but the Markov chain is sort of very simple-minded. All it uses is what state you're currently at. So it's called a memoryless process because it doesn't use any information about the past, just what you're in now, and it certainly doesn't look into the future about what the possibilities are. Now, if you want a more accurate model, you might try and do that, because it's certainly the case that when people are actually doing sentences, they do have a goal in mind for what they're eventually going to say, right? Although you might think, is that going to get you anything different than taking into account sufficiently far stuff in the past, right? Because if you well, we won't get into too much detail on this because of time, but you can think about, is looking into the future actually any different from then when you get to the point in the future looking at what you did in the past to make that decision?
How would you get yourself out of the situation where you land at Pagoda?
Oh yeah, so here you have to decide how to do that. So right now, I haven't defined any transitions coming out of this, so strictly speaking, this is not a well-defined Markov chain because it doesn't define a distribution for destination states for this one. So that's just because Pagoda was at the end of the corpus and I don't know what to do after that. So you have to decide some way of fixing that. So one way, simple way would just be add a transition, say maybe you go to some random state, uniformly at random if you get stuck there. Or maybe you always go back to the initial state or something like that. You'd have to add in transitions like that. Okay? All right, so let's go into a little bit more detail about how we would figure out which transitions to use and what their probability should be. So like in the case we had before where we were just counting tokens, we only want to make one pass through the corpus because it could be very large. So how can we efficiently work out the transitions that are leaving each state? Yeah? So a running count of what? But here we don't just want to know how often each word occurs, right? Because we want to know, like the letter A, it had 4 things that came after it, and we want to know for the word, the token man, comma, how often did it occur after the letter A? How often did it occur after the word pagoda, etc.? So we need a little bit more information here. But we still would like to do some kind of running count, that's true, because that will prevent us from having to like make multiple passes through this array. So let's think about this running count idea. Is there a good data structure we could use to store running counts, say of how often a token has occurred after another token? So let's say we've just read in one token. Okay, it was the token pagoda. We saw it came after the letter A. So now we want to update the counts for letter A to say that pagoda happened one more time after it. how should we store those counts? What's an efficient way to do that? A hash table, right? Because we have the current token, we just want to look up for that particular token. We don't know what order they're going to come in. So we don't want to keep them in a list or anything like that. We want to be able to quickly look up some information associated with that token. So we can have, or that type. So we can have a hash table indexed by the types, which then gives us the distribution which we're storing in some way. It could be a list of counts saying how often each word occurs after it, for example. Okay, right, so hash table. So let's do an example of how this might go. So let's say we've already read in A, man, A. So here's our hash table. We've got, or part of it anyway. We've got these types. They are hashed into some index of an array. And what we've seen so far is that after man, there's one occurrence of the token A. After plan, wait, we haven't, oh, sorry. After capital A, there's one occurrence of the token man. And now we're about to read in an A. Okay, so we do that. All right, that's just wind. Okay, so we read in A, or plan. And now we see that after the token A, plan can occur once. So we add that to our distribution here, or list of counts. We move on to the next thing. We get another A. So after plan, we add that A can occur once. And canal, we see that after A, canal can occur once, so we add canal in here. And then later, if we had another, if we saw canal after A again, we would increment this count from 1 to 2, say. All right? And then at the end, what we'll do is we'll convert these to probabilities by just dividing by the total. So like in this example, if we stopped here, then we would see that A is followed once by plan, once by canal. So we would add two transitions, one from A to plan with probability 1/2, and one from A to canal with probability 1/2. Oh, this thing? Yeah. I was just for simplicity here saying we just have a list, say, of entries, and we would just walk through, find the word if it's in there, and increment it, otherwise add it on the end. Could be a linked list like that, but you could also have another hash table or any kind of data structure that's convenient for storing these counts.
What if a plan happens twice?
Okay.
So is it one plan will be two plan?
Right, exactly, because we want to know how often it happens, right? Because if A occurs 3 times, and in 2 of those times it's followed by plan, and 1 of the times it's followed by man, then we want A plan to occur more often. So the transition from A to plan will give weight 2/3, the one from A to man only 1/3, because that transition from A to man only accounted for 1 out of the 3 occurrences of A followed by something. Okay? All right. So if you implement this and try it out, you'll see this gives much better results than just the dictionary sampling. But we can even do more. So let's consider a different corpus. I went left, you went right, I went left, I went right. So this is the Markov chain we learned from this. And something you'll notice here is that let's say U goes to went, and then you're equally likely to go left or right. Similarly, if it's I goes to went, and it's equally likely to go left or right. That's because went occurs 4 times, and in half of them it's followed by left, and in half of them it's followed by right. So this Markov chain is preventing some weird combinations like I went, went, so that's good. But it still is missing some information about this corpus. So you notice that I have a tendency to go left, whereas you have a tendency to go right, for example. I go left more often, you go right more often. That's not captured here, it's 50-50. The reason for that is that the Markov chain isn't looking far enough back to see who it was that went, right? It's only looking at the previous word. It says, okay, after went, when we generate went right, we only check based on the word went. So after went, right happens just as often as left. If we looked back 2 words, we would then see that right happens when we have you went, we always have right afterwards. And if we have I went, then we have left after that twice and right after it once. So we could have an even better model by using more context. And we can do that using what's called a second order Markov chain. So now in a second order Markov chain, the transition probabilities don't just depend on what state you're currently in, but also what the previous state was. So now you can use 2 states worth of information. And the way I've drawn this here is you can think of a second order Markov chain as a first order Markov chain where the states are labeled with pairs of tokens. So instead of just having 2 states in a row, we've just merged it into one where you have the history included in the state. So for example, the state I went means the current state is went, and we had previously seen an I. So given went, previously with an I that came before, then in that corpus we had before, if we go to the next one, in the corpus we had before, I followed by went is followed by left twice, right once. So we go with probability 2/3 to left preceded by went, and 1/3 to right preceded by went. Okay? Is it clear how I've notated this here? So the 2 words are saying, the bottom one is which token you're currently on, and the one above is the one you just saw. So whenever you go to a next state, the word you're currently on becomes the word you previously saw, and then the new word fills in the bottom. And now the probabilities are computed based on how often this pair of words is followed by the next word, instead of just a single word. That make sense? So you can imagine if you're going to keep track of the 2 previous words, why stop there? And indeed, you don't have to. So an nth order Markov chain has transitions depending on the n previous states. You keep track of n previous words. So what that means is that the distribution you use to pick which state to go to next, that is a function of the last n words. So this is called an n-gram. So it's this tuple of the n previous words. Given that tuple, you have a distribution for which state to go to next. I don't have a picture of a higher order one because it becomes progressively harder to draw. But I'll do a just super quick demo showing how as you increase the order, these model English text better and better. So, because you're using more context. All right, a few sentences with some repeated structure. So if I generate some words using a first order Markov chain from this, I put this down here so you can still see it. The kind of thing you get, looks like this. So it's not, incredibly ungrammatical, like you don't have repeated words at least, but it's not very good. Things are kind of mushed up, right? This doesn't make a whole lot of sense. This doesn't make a whole lot of sense. So if we use 2 words of context, so now things are a little bit better. Like, for example, you notice that you have is staying together as a unit now. You don't just, sometimes you have you appropriated, but you don't have, actually this example didn't have it, but in the old example it would be possible to have some weird things following you have. But now by using 2 words, this is quite similar to the previous thing. And if we use 3, so a third order Markov chain, it's going to be basically identical. Okay, the first one's a little bit different because I started in a random state, but this is actually a line straight from the corpus. Same. Okay, let me run another one. Yeah, it's now basically reproducing exactly the sentences from the corpus because the corpus was pretty small and so it didn't have that much variety. So if we constrain things based on the 3 previous words, there are not too many possibilities for what can happen. Okay, so let's see. Yeah, we have a little bit of time. So one thing that is interesting to see here is higher order chains are going to model English better, but they do have a downside. So, or several downsides. So can someone think, what's a problem with using like a 12th order Markov chain, something like that? It will sound the same many times? Or it won't? Well, so if you have a small corpus, certainly. If you have a big corpus, there are more possibilities, but it's true that if you're using things based on the previous 12 words, it may be too constrained. That's certainly possible. And related to that, there's the issue that you think of how many possible combinations of 12 words there are, right? Like 12 grams. If you have W different words, then there's going to be W times W times W, W to the 12th possible 12 grams. So there's a huge number of those. But how many possible 12 grams can actually occur in a corpus with like L tokens? Yeah? Oh, so you use a different number each time? Yeah, that's an interesting idea, and there actually are more sophisticated models that do that. That's a good idea because sometimes you can imagine that in some cases going back quite far is necessary because you have some idiom that always goes a certain way, but other times more randomness would be allowed. Yeah, you absolutely could do that. But going back to the question I asked, let's say you have a corpus of L tokens. How many possible 12 grams can you get out of that corpus? Asymptotically. Let's not worry about off by 1 and stuff like that. It's L minus 12 or something very close to that, right? Because you just break the text up into blocks of 12 shifting along. And each one of those is a 12 gram, right? You can't get any other ones because you're not like mixing the words around when you count 12 grams. So you only have a linear number of 12 grams that you can get from the corpus, right? But the total number of possible 12 grams given W different words is W to the 12th, which is going to grow much faster, presumably, right? So if you use a very high order Markov chain, unless your corpus is massive, the Markov chain you're going to learn is going to be very sparse because it's going to, there's a huge potential space of states, right? W to the 12 states, but only basically L are going to actually be used. So you may not end up getting good results out of that chain. Okay, so let's talk about how we would learn one of these higher order Markov chains. So now we have to keep track of the previous n tokens instead of just one previous token, right? Because we want to know, let's say it's a second order Markov chain, we want to know, given that the words will have just occurred, what's the probability of any third token occurring? So one possibility is just, okay, you back up and reread those characters, or those tokens whenever you need them. But another one, which I'll mention because part of the project is to get you familiar with data structures, is to use a queue. So a queue, which is also called a FIFO buffer, that's for first in, first out, is like what the name entails. It's a queue, a line that you could stand in. So maybe 0 starts out in the line, 1 and 2 get added in, but they still have to wait for 0. Okay, 0 finally gets to go through, so 1 and 2 move up. 3 gets added on maybe. Okay, 1 gets to go, 2 and 3 move up, and we add some fourth one in. So that's what is happening in a queue. Things get added on or enqueued at the back, but they have to wait. People will get dequeued, removed from the queue, in the order that they were originally added. That's why it's called first in, first out. Okay? So the kinds of things you would do with this queue are, in queue, you added something at the back. You dequeue, you take off the thing at the front, the guy who's been waiting the longest. And you might want to iterate, go over everybody who's currently in the queue. So can someone describe why a queue might be useful for learning an nth order Markov chain? So if we've got an nth order chain, right, that tells us, a Markov chain, for every state, there's a distribution on states that you can move to. But that's a function of the state you're currently at for a first order chain. For an nth order chain, it's a function of what? Well, so what are the things that the transition depends on? Like, if it's an nth, it's the current state you're in in a first order chain. But in an nth order chain, there's more information.
Previous n tokens?
The previous n's, yeah, tokens, or tokens in our case, but states in general, right? Given the n states you've been in most recently, that's what tells you what the probabilities are for going to the next state. So what we need to keep track of are what the last n states are. So how can a queue help us with that? Right. So if we keep the states that we've been in a queue, whenever we reach a new state, we in-queue it, then they're just going to accumulate, right? Eventually, this queue is going to get up to size n. From then on, whenever we in-queue a new state, if we dequeue a state, then it will still have n things, because we were at size n, we add one on the end, and we remove one from the front. And because a queue removes things from the oldest first, right, the things that have been waiting in line the longest, this will ensure that what's in the queue are the n most recent tokens we saw. Because we're pushing them into the queue, or in-queuing them in the order that we saw them, and then we remove them in that same order. So the oldest things get removed first, so that way the queue will always keep track for us of what the n most recent elements were. Make sense? Okay, so leave it up to you to think about how you can implement a queue. That's basically the material. I just want to mention a couple of further directions in case you're interested. If you think Markov chains are cool, there are a huge number of applications of them. I just want to mention one because it's a very important application which has influenced your lives at least a little bit because you've used Google. So Google's original ranking algorithm for how to sort the items that come up in the searches called PageRank models user behavior as a Markov chain. The states are web pages, the transitions are links. And the idea in PageRank is we'll treat a person browsing the internet as doing a random walk on that Markov chain. And then we'll work out which sites they're most likely to spend the most time on, and those sites we'll put higher up in the ranking. And it's a little more sophisticated than that, but that's the basic idea. So the reason Google's search was so much better than its rivals, at least when it first came out, was because of this algorithm, where you're modeling what the human being using the internet is doing as a Markov chain. Of course, that's an approximation, right? Because people aren't using just the current site you're on to decide which link to hit next, right? But it's an approximation that is scalable. They were able to use a huge Markov chain. I mean, one state per page on the internet, right? So even in the early days, that was a huge number of states. But using some clever algorithms for implementing random walks, you can do it. Another direction, if you're interested, that you can do is variations on the queue data structure. So one is a circular buffer. Notice in this case, we never need to store more than n things in the queue, right? So if you know ahead of time how much space you're going to need for the queue, like a normal queue, you could just keep adding things. It gets big, the line gets longer and longer. In a circular buffer, you know, okay, I'm never going to have more than n things at once. So there's a different, you can implement it in a more efficient way, taking advantage of the fact that you never have to allocate more memory or something like that. So you might think about how you could do that. Another extension is the deck, or the double-ended queue. That's where you can not only in-queue things on the end, you can in-queue them on the front. And you can remove them from either end as well. So you can think about how to implement that using some data structure you've already seen. And then a much bigger extension is to a priority queue. So some of you may have done the part of the tutorial where you work a little with heaps. Heaps are one way of implementing a priority queue. That's where you can push things on, but the order that you get them off is not the order you put them on. The order is in priority order. So every element has a number saying how high priority it is. And you remove things in order of priority. So if I have a bunch of things waiting in line, if I suddenly push a very high priority thing, it can get removed earlier than all the things that were waiting longer than it was, because it's higher priority. And what's more, a priority queue allows you to change the priority of an item that's in line already. So maybe someone's been waiting in line for a while, you suddenly move them to the front of the line. So you can see this is going to require a more sophisticated implementation, so you can think about how you might want to do that. Okay, So I think that is basically it for the material. Are there any questions on anything we covered today? Okay, well, I'll be here for at least a little while if you have individual questions, and as Jeremy said, I think we should be making available, the slides certainly will be available, and my contact info should be as well if you have any follow-up questions. But that's it, thanks.